Hello, I'm Dr. Dupre, and in this section we're going to discuss space coordinates and vectors in space. One of the most useful ideas in mathematics is the idea of a vector, and that's mainly because vectors are so geometrical on the one hand, and yet on the other hand can be computed algebraically. In other words, vectors provide us a very fast way to go back and forth between geometry and algebra. In order to do that, you want to have very clear pictures in mind as to what vectors are and how they work. So let's look at the basic geometric pictures that we want to keep in mind. So to begin, we think of a vector as an arrow in space, and here I've drawn an arrow in space which I've denoted with V with a little arrow symbol over the top. And the thing to keep in mind is the important aspects of a vector are it has direction and length, or what's often termed magnitude, and those are the only two properties that are important. That is, if the vector is shifted to another position in space but its direction stays the same and its magnitude stays the same, then it's the same vector. We don't distinguish between these two arrows that I've drawn. They're pictures of the same vector. Now, here I've used for notation the little V with the arrow over the top. When we're writing on paper or drawing at the board, we use symbols with little arrows on top to denote vectors. Typically in textbooks, vectors are denoted in boldface, especially in calculus textbooks and physics and engineering. Now, vectors can be added, and the simple way to add geometrically for the geometry of vector addition, it's simply head to tail. So in this picture, I have two vectors, V and W, and you don't have to think of them necessarily as being in the plane of the blackboard. They could be perspective pictures of vectors at odd angles. In any case, to add them head to tail, V plus W, we just take W, move it so that its tail is at the tip of V, and then connect the tail of V to the tip of W, and that result, often called the resultant, is the sum V plus W. This is a very convenient way to add vectors and pictures, and so here, for instance, I've shown a picture of the way we could add three vectors, U, V, and W. I would just take the tail of V, shift the vector V so that its tail is at the tip of U, shift the vector W so that its tail is at the tip of V, and then I connect the tail of U to the tip of the last vector W, and that resulting arrow is the sum of all three. And notice, for instance, we could think here of U as maybe angling out of the blackboard some, and V goes down, maybe angling back a little, and then W goes way back. And so this resulting arrow will actually be connecting behind the V, you see, so it's going behind it, which I've indicated with a little space here so that the arrow V picture comes in front of this resulting sum, which is U plus V plus W. Now, the parallelogram law for addition is another useful way to think of addition happening, and for that picture we put the tails of the two vectors together. In other words, we just shift them, keeping them parallel to themselves, leaving their lengths unchanged, but put their tails together, and then you draw a parallelogram using those two vectors as sides. Now notice, here's the vector V, and shifting up to this edge of the parallelogram, there's V again. And whereas if I take W and shift it over this way so that its tail's at the tip of V, there's W again. So when I add this head to tail, I'm forming W plus V, whereas if I add them this way, it's V plus W. In other words, V plus W, the resulting sum, is the same as W plus V. It does not matter in what order we add vectors. We can add them in any old order we want, and the result's the same. And using head-to-tail addition, you just connect them all up, head to tail, however many, draw an arrow from the tail of the first to the tip of the last, and you have the picture of the sum. Now, when we want to be more accurate in dealing with vectors, we sometimes want to deal with particular points in space for their tails and tips, and the notation there is for PQ with an arrow over the top, where P and Q are points in space. That's the notation for the vector having tail at P and head at Q. So if here's the point P in space and here's the point Q in space, that arrow with tail at point P and tip at point Q is going to be denoted PQ with the arrow over it. Now, let's look at how we can use points in space to describe vectors more accurately, and how we coordinatize points in space using rectangular coordinate systems. Here in this picture, I've drawn 3 mutually perpendicular axes passing through the same point, which I've denoted capital O. Think of this as Y and Z in the plane of the blackboard, and X comes straight out at us. This is what we would call a right-hand coordinate system. That is, if I put my hand so that my thumb is pointing along the x-axis and my fingers stretched out are pointing along the y-axis, when I curl my fingers up to a right angle, they're going to point along the direction of the z-axis. And so that's telling me I have a right-hand coordinate system. If I did that with my left hand, it's not going to work. See, if I put my left hand there with my thumb pointing in the direction of the positive x-axis and my fingers pointing in the direction of the positive y-axis and curl my fingers down, it goes the wrong way in the negative z direction. So if I have any point in space, call it capital P, we're going to denote its coordinates A, B, C. And how do they relate to this picture? Well, I can imagine a little box whose sides are parallel to these coordinate axes. The edges are all parallel to coordinate axes. For instance, to begin, from the point P, drop a perpendicular to the plane of the x and y axes, and then take that point in the xy plane and project to the x and y axes respectively, and I'll get a number A on the x-axis, a number B on the y-axis, and likewise projecting horizontally over to the z-axis, I get a number C on the z-axis. So, for instance, this point has coordinates in space A, 0, 0. This point has coordinates 0, B, 0. And then this point has coordinates A, B, 0, just like the first 2 coordinates are the ordinary xy coordinates for this point in 2-dimensional rectangular coordinates. And then we have the z coordinate 0. And up here, this point is 0, 0, C, where you've hit the point with z coordinate C on the z-axis in effect. And this point then has coordinates A, 0, C. This point has coordinates 0, B, C. And then finally this point, the point of the box that's diagonally opposite the origin, has the coordinates A, B, C. So it's using pictures like this that we can draw easily perspective pictures of coordinates for points in space. Now, for instance, if I draw an arrow whose tail is at the origin and whose tip is at the point P, and we denote that arrow as a vector OP, then since it's completely specified as an arrow by the fact that its tail is at the origin and its tip has coordinates A, B, C, that means we've nailed down what that vector is, and we denote that with angle brackets A, B, C. And we keep those angle brackets there to remind us that it's the symbol for a vector. And so if we want to relate that vector to points in space right from its coordinates, these numbers we call the components of the vector, V in this case for short for OP. To relate that, what we have to do is think of its tail as being at the origin O, which of course has simply 0, 0, 0 for coordinates. Now when I look at this picture, For instance, notice right off, I can have a vector whose tail is at the origin and whose tip is at the point A, 0, 0. And then I can have the vector whose tail is here and whose tip is at the point A, B, 0. And then I can draw a vector whose tail is at A, B, 0 and whose tip is at P. In effect, right away I see this vector OP, which I've called little v with an arrow on it, is the sum of three vectors, and clearly they're completely uniquely determined by the point P here. The first vector is along the x-axis. The second vector is parallel to the y-axis with tip at the tip of the tail at the tip of the previous vector. And then the last one comes vertically, straight up, and its tail is at the point A, B, 0, and its tip is at A, B, C. And look, head to tail, that means OP is the sum of these three vectors. And of course, this vector is the same as this vertical vector here right in the z-axis, and this vector is the same as this vector. In other words, the vector v itself is clearly the sum of three vectors, each one parallel to the axes. We've got the vector along the x-axis, vector along the y-axis, vector along the z-axis, and they add up to OP. Well, for scalar multiplication, that is multiplying by numbers, if I take a unit vector in the direction of the x-axis and a unit vector in the direction of the y-axis and a unit vector in the direction of the z-axis, then this vector is A times this vector of unit length. This vector is B times this vector of unit length. This vector is C times this vector of unit length. And it's customary to denote those unit vectors along the axes with I for the unit along the x-axis, J for the unit along the y-axis, and K for the unit along the z-axis. And so we have A times I plus B times J plus C times K is V. So another way of thinking of this component notation for the vector, when you see angle bracket A, B, C, that's the same as A times vector I plus B times vector J plus C times vector K. And remember, I, J, K are the unit vectors along the X, Y, and Z axes respectively. So we can turn computations involving vectors into computations with numbers using these components. Now let's plot some points in space on a rectangular coordinate system. It can be a little trickier at first than in just 2 dimensions because we have to deal with the third dimension, which can't be actually specified in 2 dimensions unless we go to a perspective picture. So what we want to do is plot the points 1, 2, 3, negative 1, 2, 3, 1, negative 2, 3, and 1, 2, negative 3 on the same coordinate system. So here I've drawn a rectangular coordinate system. Remember, the x-axis you're to think of as coming out of the blackboard straight at you, and consequently I've drawn it in a perspective drawing as if we're viewing it from over here. In other words, the axis is coming straight out, we're over here, and so it appears to kind of angle off to the left. I've chosen a unit the same along all the axes, and since y and z are in the plane of the blackboard, it appears the same along each of the y and z axes. But because the x-axis is drawn in perspective, its units are foreshortened, and so the hatch marks denoting 1, 2, and 3, and negative 1, negative 2, negative 3 appear closer together in the perspective drawing. And it's the use of this perspective drawing that enables us to actually visualize where these points are. So let's begin. We'll plot 1, 2, 3. So we come out 1 along the x-axis, and now we're going to come 2 along the y-axis. And so in order to do that, well, imagine I came directly parallel to the y-axis from this hatch mark on the x-axis. On the other hand, suppose I came parallel to the x-axis from this point. These two lines cross, and there is the point whose coordinates are 1, 2, 0. And so now I want to go 3 units vertically. Well, to picture that, this would be 3 units vertically on the z-axis. Come over here 2 units to the right. And so this point right here has coordinates 0, 2, 3. And now come forward from this point straight out of the board, but in our perspective drawing, we want to draw that parallel to the x-axis. And here coming up from this point, that's where we'd meet, doing likewise going up 3 units from this hatch mark on the x-axis and coming again parallel to the x-axis here. Well, you see we get our picture of our little box, and when I look at that box like that with the dashed lines, I can now visualize that this point with coordinates 1, 2, 3 is sort of perspectively in front of the board that we're looking at. Now, what would be the effect of replacing the x-coordinate 1 by a negative 1? Well, that would mean we would be marching back this direction, back to this hatch mark. And so coming over to, we would then result in this box. And so right here would be the point with coordinates negative 1, 2, 3. It's behind the blackboard by 1 unit. Whereas if I change the y-coordinate to negative 2, that would mean coming back this way 2 units, still 1 in front of the blackboard. And so our box then looks like this. And so here's the point with coordinates 1, negative 2, 3. And what about changing the z-coordinate from 3 to negative 3? Well, that would be instead going down 3 units. In other words, instead of coming over here and going up 3 units, we go down 3 units. And to remember, coming off the negative 3 mark on the z-axis, we want to kind of move parallel to the x-axis, and then parallel to the x-axis. And so this point right here, you see it's kind of 1 unit in front of the blackboard, 2 units to the right of the z-axis, but 3 units below the xy plane. And so with the dashed lines there, you can kind of get an idea in perspective of where those points are, even though we're only looking at a 2-dimensional picture. Well, let's see how we express the length of a vector given to us in terms of its components, how we express the length in terms of those components. So for notation, when you see a vector notation V with double bars on either side in the textbook, that typically denotes the length of a vector. In some textbooks it's only a single bar, but more commonly nowadays we use double bars. So if the vector V has components A, B, C, denote here we have the angle brackets to remind us that's not just a point in space, as are components of a vector. So in terms of the unit vectors I, j, k, it's AI plus bj plus ck. Well, the formula for the length of V is very simple, just the square root of the sum of the squares of all the components. In particular, that means if I square the length, I just get the sum of the squares of the components. Notice if I take the vector A times I, that's pointing out from the origin along the x-axis, think of it like that, and then bj parallel to the y-axis and ck going up vertically. Well, notice right here, I've drawn, we have a little right triangle down there, and the horizontal plane, and this point here where the tails are set, we draw a line from that point out here to the tip of BJ, and that's the hypotenuse of a right triangle. So the square of that distance is a square plus b square. And now notice here we have another right triangle. So the length of the hypotenuse squared, which is the length of v squared, is the square of the vertical side, plus the square of the horizontal side, which was a square plus b square. So that means the total for the squared length is a square plus b square plus c square. It, in effect, is just a consequence of the Pythagorean theorem for getting the length of a hypotenuse of a right triangle in terms of the lengths of the sides. Well, let's apply this. So, for instance, let's find the length of the vector v whose components are 2, 6, 9. So the length of v is the square root of 2 square plus 6 square plus 9 square, which is the square root of 4 plus 36 plus 81, which is the square root, well, 4 and 36, that's 40, and 81 is 121, and we recognize that 121 is the square of 11, so the square root of 121 is 11. So this vector has length 11. Well, how can we deal with the situation of points in space and use this to our advantage? Well, if I have 2 points P and Q in space, then it's the fact that the vector from P to Q is OQ minus OP, where O is the origin. So here I've drawn a picture showing the origin and the 2 points in space, the origin of whatever coordinate system we're dealing with. And so consequently, from O to P is the vector OP, from O to Q is the vector OQ, and from P to Q is the vector OPQ. Now notice, head to tail addition, OP plus PQ is OQ. So let's write that. OP plus PQ is OQ. So if I solve this equation for what I'm interested in, PQ, it tells me PQ is OQ minus OP. That's real easy to remember in terms of that picture. So that means if I have the coordinates of the points P and Q, for instance, suppose P has coordinates A, B, C, and Q has coordinates X, Y, Z, then what I want to do is subtract the vector OP from the vector OQ. So writing one on top of the other for ease of reference, remember to subtract vectors in terms of their components, you would just subtract like components. So the first component is X minus A, the second component is Y minus B, and the third component is Z minus C. And so that's very easy. Well, notice what happens if I want to find the squared distance from P to Q. That's just the length of the vector PQ squared. So that's X minus A quantity squared plus Y minus B quantity squared plus Z minus C quantity squared. And so that would tell us then that the distance from P to Q, being the length of the vector PQ, is simply the square root of all that. So we have X minus A quantity squared plus Y minus B quantity squared plus Z minus C quantity squared. And I want you to notice, even though this formula may appear complicated at first, notice how easily it comes out just from the geometry of the vectors. We just look at the little triangle picture, and it reminds us that to get the coordinates, the components of the vector PQ, we subtract one from the other, and then we have a vector P to Q whose components are expressed as differences of the coordinates of the corresponding points, and so then the squared distance is the squares of the sums of squares of differences of components, and so now we get the length with this square root formula. In other words, once you know how to interpret equations in terms of vectors, it becomes very easy with a few simple rules to translate those things into equations in terms of algebra. You go from geometry to vectors to algebra. 2 steps and everything becomes very easy. Now let's look to see how we can use our formula for the distance between 2 points, thinking of it in terms of vectors, to analyze the equation of a sphere. All right, so the problem we have here is we want to find the center and radius of the sphere with the equation x squared plus y squared plus z squared minus 4x minus 8y plus 6z equals 7. Now, of course, that looks like a pretty big equation when you look at it at first, but the thing that jumps out at you is that it's quadratic. We have linear terms, constant terms, and squares. And so the technique we use to understand it is called completing the square. So let's review how you complete the square. If you have a sum of 2 terms, ax squared plus bx, in other words, a quadratic and a linear in the variable x, what we begin by doing is factoring out the coefficient of the square term. And so in this case, we have a times the quantity x squared plus b over ax. And now what we do is we ask ourselves, how can we express this as a square, at least up to a constant? Notice if I square x plus b over 2a, I'll have x squared plus b over 2a quantity squared, which is b squared over 4a squared. So I would have added that, and it doesn't appear up here, so I subtract it. But what's the cross term? Twice the quantity b over 2ax, which is exactly b over ax. So in effect, this is equal to all of that. And notice that what I now have is a multiplied by something which is simply a square of a simple linear term in x minus a constant. Well, let's apply this to our equation. So here I have the equation written again, x squared plus y squared plus z squared minus 4x minus 8y plus 6z equals 7. And to begin, let's gather the like variables together. That'll make it easier to see how to complete the square. So x squared minus 4x, write those together. Y squared minus 8y, I'll gather those together. And the z squared plus 6z. And so all of that equals 7. So notice, to complete the square, we just look at the coefficient of x and divide by 2. So we have x minus 2, quantity squared. Now, what did we just add if we replaced this by this? We just added 2 squared. In other words, if I square this, what do I get? X squared minus 4x plus 2 squared, which is 4. So if I try to replace this by this, I would have added 4. So let's subtract 4 to make up for that. Likewise, right here, y squared minus 8y, divide the 8 by 2, we have y minus 4, quantity squared. If I were to simply replace this by this, I would have added 4 squares. So to make up for that, I subtract 4 squared, which is 16. And then likewise, what's half of 6? To complete the square on the z terms, that's z plus 3, quantity squared. Notice, if I square that, I get z squared plus 6z plus 9. So we would have added 9, we have to subtract 9, and all of this still equals 7. Now what I do is I take all the constant terms and move them to the other side of the equation. And the equation has this form, x minus 2 squared plus y minus 4 quantity square plus z plus 3 quantity square equals 4 plus 16 plus 9 plus 7. So finally, x minus 2 quantity squared plus y minus 4 quantity square plus z plus 3 quantity square equals 4 and 16 is 20, and 9 plus 7 is 16, 20 and 16 is 36. Now, we can look at this and see right off, in terms of our formulas, we know this is expressing the distance from the point x, y, z to the point 2, 4, negative 3. The squared distance is 36, so the distance is 6. That is, it's a sphere of radius 6. Let's look in terms of vectors. Notice this sum of the squares is the squared length of the vector with components x minus 2, y minus 4, z plus 3. And I'll write the 36 as 6 squared. And so notice we've got differences in the components, so it's obviously the vector with components x, y, z, minus the vector 2, 4, negative 3, negative and negative is plus, length equals 6. So when I take the equation, complete the squares on each of the variables separately, and write it in vector terms, what's it saying? It's saying, in effect, the length of the vector from 2, 4, negative 3 to the point with coordinates x, y, z is 6. Well, we know that expresses the equation of a sphere which has radius 6, namely all points x, y, z, whose distance from the fixed point has a fixed radius. In this case, the fixed point is the point with coordinates 2, 4, negative 3, and the fixed distance is 6. So the 2, 4, 3 is the center, and 6 is the radius.